All right, we're finally here. This is it. We're finally do some calculus, okay? And it's very brief, okay? Integrating to get rotational inertia, okay? The actual way to get rotational inertia is this integral right here, I equals r squared dm. And what it represents, okay, is just like all integrals, you split object into tiny pieces of mass dm. Okay. The second step is that you multiply, okay, each piece by r squared, okay, or distance from the axis, okay, distance from axis, okay, to get that piece's uh, inertia di, okay? And then the third step is to add up all the di's, okay, to get total I. Okay, so that's what you're doing. Now that's one integral that you can use, but I'm actually going to show you an easier integral to use because it's just way easier. Okay, it's the integral of r squared times the density, the linear density of the object, dr. This is an easier integral to use because a lot of times the integral will require you to make this stop first before you can actually solve the problem. So even if you just use the basic one, you oftentimes will have to go through this one first. So you might as well just remember this one. This is not provided, but you should remember it, okay? Density of, or sorry, row of R is what we call the linear density, okay? Here's how we get it. Okay, here's how we get it. It's a really silly derivation. Okay, really silly. Okay. I've got this, that the moment of inertia is the integral of r squared times dm. Okay. Well, guess what? Let's say that I want to multiply both sides by 1 just for fun, right? If I multiply it by 1, nothing's going to change, right? Well, 1 is the same as saying 2 over 2, or 3 over 3, or 4 over 4, or maybe it's the same as saying, I don't know, dr over dr. And when you do that, you end up getting this new integral, which is r squared times dm over dr times dr. Okay? Well, this thing right here that you just got, dm over dr, that's literally the linear density. Okay? That's literally linear density. And so then you would get I equals integral r squared times the density function with respect to r dr. Okay? And you can actually, this is way easier to integrate, and I'm going to show you why that's way easier to integrate. Okay? Show that the rotational inertia of a rod about one end is 1/3 ml squared. This is really easy to show. Okay? So if I have a rod, okay, and I decide that I want my axis to be the left end, okay, that's my axis, okay. Well, you're going to notice, okay, what I'm going to say about the length or the distance, right? This is r equals 0, and this is going to be r equals L, which is the length of the rod, right? So what I'm going to do is I'm going to start with that density equation, okay? Actually, I'm going to start just with I equals integral r squared dm over dr, okay, times dr. The density is, so dm over dr is just m over L, okay? dm over dr is just m over L, okay? So that's what I'm going to do. I'm going to replace that, okay? And I get integral r squared m over L dr. And then you're going to notice, wait, m over L is a constant. Okay? So I can take that out. Okay? Times the integral of r squared dr. And wait a minute, then r squared dr is a super easy integral. Okay? But I have to apply bounds to it. I want to take this integral from the rod with r equals 0 to r equals L. Okay? So I have to apply my bounds to it. And then when I integrate, I should end up getting, okay, I equals m over L, okay, and then r cubed over 3, and I have to go from 0 to L. Okay, and then I apply the fundamental theorem of calculus. But wait, if I replace the r with 0, this whole thing becomes 0. So I actually can completely ignore that lower bound. The upper bound is still important, though. So I should get I equals m over L, okay? And then when I replace L here, I end up getting L cubed over 3. And then you should notice that, hey, one of my L's here can cancel out with the L down here, and I end up getting m times L squared over 3, which is this equation right here, okay? 1/3 ml squared. Okay, beautiful. We just proved that. Okay, this one there's a typo. It should say that the rotational inertia of the rod about the center of mass is 1/12 ml squared. Okay, and I'll prove that for you too. Okay, I'm actually going to start out in a shortcut way. I'm actually going to start from the second step right here. Okay, and I'm just going to bring that over. Okay, so I'm going to do I equals integral r squared m over L dr. Okay, for this case, the rod actually, the length is going to be a little bit different, or my bounds are going to be a little bit different. You know why? Because right here in the center that's my center of mass. Okay, and then you're going to notice that the rod has a length L, but here's my axis. Okay, the rod has length L. However, this is not going to be. It's not going to go from 0 to L anymore. It's going to go from r equals -1/2 L to r equals +1/2 L. Okay. It's kind of weird how that works. So when I apply my bounds, they're going to be a little bit different. They're going to go from -1/2 L to +1/2 L. Okay. And when I do that, I end up getting m over L integral r squared dr, which ends up becoming m over L. Sorry, I forgot to apply my bounds. -1/2 L 1/2 L. Okay. Can hardly see that because I kind of scribbled it in there. Becomes r cubed over 3 from -1/2 L to 1/2 L. All right. Okay. So there's that. Okay. And then when I apply my bounds, okay, when I apply my bounds to this, I end up getting that the inertia should be equal to m over 3L, okay, because I factored out my 1 over 3. It times, let's see, is going to be L over 2 cubed, okay, minus, oh sorry, I actually don't need that bracket right there, minus m over 3L negative L over 2 cubed, okay? And then when I end up doing this, right, so you're going to notice L over 2 cubed is going to be L cubed over 8, and it's going to be L cubed over 8 as well. And then you have to multiply, or there's also going to be L cubed over 8, but it's going to be negative because negative cubed is still negative, okay? And that actually turns this part into positive, okay? So when you actually do all of that, you're going to end up getting ml cubed over 24L plus ml cubed over 24L, okay? Well, what you can notice here, right, is that one of your L's has to cancel out on both of them, okay? And so you would end up with 2 ml over 24 if you add those properly. 2 ml squared over 24. Okay. And that ends up being 1/12 ml squared, just like your typical inertia equation. Okay. Okay. Now, this was a problem on a Physics C test a while ago about a triangle that is rotated about an axis. Okay. Or I guess it's not rotated about an axis here yet, but it's talking about rotational inertia for a triangle. Okay. You're given the density function, which is great. Okay. To find the mass really quickly, I'm going to do this one really quickly. All you got to do to get the mass, okay, is use m equals, well, m is technically just the integral of dm, right? Well, that doesn't tell us anything, okay? But if we multiply by dr over dr, okay, that will then become that m is equal to the integral of the density function with respect to r. So now I can just take my density function, which I'm given up here, okay, and I just do m equals the integral of CHR over L, and I'm going to do this from 0 to L for the length of the triangle, okay, dr, okay. And you'll notice that CH over L is constant, so this really just becomes CH over L integral L, or from 0 to L of R dr. Okay. And then all you got to do is integrate the R, and it's not that bad. So you would just do CH over L. Fundamental theorem of calculus gives you, or fundamental theorem of calculus is what you would do next, I guess. Okay. And you'll notice that when you apply the zero bound, this becomes zero, so it really doesn't matter. It really just becomes CHL squared over L 2L. Okay, so this really becomes m equals CHL squared over 2L. Okay, and then you cancel out the L's, and you end up getting that mass is just equal to 1/2 CHL. Okay. Okay, and then for the rotational inertia, again, I'm going to do the same thing. Okay, I'm going to use the integral I equals r squared times rho of r dr. Okay, when I plug that in, I'm going to integrate from 0 to L. That's going to give me r squared, okay, times the density, which is CHR over L dr. Okay, and you can notice that I have r squared r. So now this really just becomes, okay, I can factor out my ch over L, okay, integral from 0 to L of r cubed dr. Okay. Plug in your bounds or integrate, plug in your bounds, you end up getting ch over L integral. The integral of r cubed is just going to be r to the 4th power over 4. Okay. And then you do have to plug in your bounds, which the zero bound still makes this whole thing 0, so it doesn't even really matter. Okay. So you end up getting I equals CHL to the 4th, okay, over 4L. And you'll notice, bring this down to 3, cancel out the L, and you end up getting 1/4 CHL cubed. Okay, now this is the part where this part comes important because it wants to say, how can we use these results to find the rotational inertia of a cylinder is equal to this? And there's an easy way to prove that. Okay, if you take a bunch of triangles and stitch them together, you actually can make basically a cylinder. Okay, it's not perfectly a cylinder, but it's basically a cylinder. Okay, okay. What I'm going to do is I'm going to take my mass that I got earlier. Okay, mass is equal to 1/2 CHL. Okay, And if I get c by itself, which c, by the way, is some constant, usually it stands for like the thickness of the object, okay? If I multiply by 2, divide by HL, then I end up getting that c is going to be equal to 2m over HL, okay? Now that's important because then I can plug it back into my inertia equation, okay? And when I do that, I will get the inertia is equal to 1/4, plug in my c, which is 2m over HL, okay, times HL cubed. Huh. And then a ton of stuff is going to cancel out here, right? This is going to turn into 2. This is going to cancel out to 1, so it doesn't matter. H's are going to cancel out, okay? And then the L is going to cancel out with one of the L's up here, which actually just gives you I equals 1/2 ml squared, okay? Okay. Now, you can actually turn this without any issues into 1/2 mr squared because if you take the pivot point, right? Well, L is the length, they call it the altitude of the triangle, okay? That's the same as the radius of the cylinder, right? Does that make sense? Okay. All right, well, that is integrating to get rotational inertia, and that's the end of this unit. So live, laugh, love, live, laugh, lab, okay?